Welcome to today's video. Today's topic of discussion is quite fascinating. Building quantum computers with antimatter. Sounds impossible, right? Yes, it sounds impossible because we are talking about antimatter. How to make quantum computers with antimatter? That is the topic of discussion in today's video. Is that possible? Is there any chance? Is there any possibility of making quantum computers with antimatter, not matter? So you know quantum computers, the matters are used, okay? Particles like electrons, those things are used. Tiny particles, rather I should say tiniest particles are used which follow the principles of quantum mechanics. Particles which follow the principles of quantum mechanics. That means what? Especially quantum superposition, quantum entanglement. So, as for example, I can say that electrons are there, protons are there. Okay. So, those things follow quantum superposition, quantum entanglement. And by harnessing those principles of quantum mechanics, quantum computers are made. That is known to you. But here the question is whether it is possible to make quantum computers with antimatter instead of matter. We are talking about antimatter. Instead of electron there will be positron, instead of proton there will be antiproton. Is that possible? The answer to this question is yes, this is possible. But question is how? First, how is that possible? Because answer to this question is yes. I have already mentioned that answer to this question is yes. Antimatter, they are just opposite to normal matter. That is known to you. And charges are opposite. They are same as normal matter. Actually, they are opposite to normal matter in what sense? Sense is charges are opposite. Masses remain the same. Such as for electron, positron is there. Electrons are negatively charged, positrons are positively charged. Protons are positively charged, antiprotons are negatively charged, but masses remain the same. Okay, charges are just the opposite. And the positive point, and that's why scientists are thinking like that, it is possible to make quantum computers with antimatter because antimatter particles also follow the principles of quantum mechanics. That is the advantage. That is the positive point. Antimatter particles also follow the principles of quantum mechanics. That means they also follow quantum superposition, quantum entanglement, quantum coherence is there, quantum tunneling effect is there. So all these things are obeyed by antimatter particles also. That means there is no problem making quantum computers with antimatter. But still there is a problem. So challenges are there, again advantages are there. Both are there. So in near future we can see the use of antimatter in building quantum computers. Okay, so what are the challenges? First let's discuss about the challenges. What are the challenges? Challenges are that producing antimatter is so expensive. Massive particle accelerators are required, like a Large Hadron Collider. Massive particle accelerators are required just to produce a few nanograms of antimatter. That massive particle accelerators are required. So that is quite challenging. Next, you know that when antimatter comes in contact with matter, our Earth is made of matter. Our planet Earth is made of matter. So, where we develop technologies, all are made of matter. So, how antimatter you can use with matter? Because you know that when antimatter comes in contact with matter, annihilation occurs. And there is a release of energy. Enormous energy is produced during the annihilation process according to the formula E is equal to mc square. You can easily calculate. and in the form of gamma rays the energy is produced. Okay, that is known to you. So how to handle that antimatter? That means there is a requirement to isolate that antimatter particles. While you are using that antimatter particles for building quantum computers, isolation of that antimatter particles is required. But that is possible. That is not impossible. That is possible. To do that thing, you need vacuum chambers, you need electromagnetic traps. Means you have to make electromagnetic traps as well as vacuum chambers are required. Okay. So by the help of those things, you can isolate the antimatter. So that way the problem is solved. It means that way you can solve the problem of annihilation. Next, you know antimatter, when comes in contact with matter, it produces enormous energy. So that is one advantage. What is the advantage? By using that annihilation energy, you can power the quantum computers, because to run the quantum computers, to operate the quantum computers, power is required. So that power may come from the annihilation process itself. So that is the advantage. But again there is one challenge. What is the challenge? Challenge is storing antimatter is a daunting task. No doubt is a daunting task. Okay, but advantages are there. One thing is, whenever you are making electromagnetic traps for the isolation of antimatter, that creates an environment which is free from external disturbances. You know that qubits are used in case of quantum computers. Traditional computers use zeros and ones as bits, but quantum bits or qubits use zeros or ones or any combination of both. Okay, at the same time, any combination of both at the same time. Qubits use that thing, zeros or ones or any combination of both at the same time. But the problem with qubits is that qubits get easily disturbed by the environmental noise. That is a problem. And if qubits get disturbed by the environmental noise, in that case, erroneous result might be produced by the quantum computers. Erroneous results. But whenever you are using antimatter to build quantum computers, in that case, antimatters are already isolated. You have used electromagnetic traps to isolate the antimatter particles, which are forming the qubits for your quantum computer. So since those antimatter particles are isolated, that means they are free from external disturbances. So error-free computation would become possible by the help of antimatter. Whenever you are using antimatter for building quantum computers, in that case, error-free computation would become possible. Though it is still it is so challenging, because I have already mentioned the main challenge is not electromagnetic traps. Means main challenge is not isolation of the antimatter particles. Main challenge is the cost of production of antimatter. Because in the universe, antimatter is rare, and if you produce it artificially, then it is very expensive. Just to produce 1 gram of antimatter, billions of dollars is required. Okay. So the problems are there, means challenges are there, again advantages are there, and the field of particle physics is advancing very well. Means a rapid progress is there in the field of particle physics. And if achieved, if we really could produce quantum computers with the help of antimatter, in that case the field of material science, there will be a rapid progress in the field of material science, in the field of artificial intelligence, in the field of drug discovery for new diseases or for existing diseases. Okay. At present, antimatter could be used in case of energy production, in case of advanced medical imaging, but at present, antimatter particles are not being used to produce quantum computers, to make quantum computers. Okay. In different fields, you know, PET scan is there. Positron particles are used. Positron is what? That is antiparticle. Means antimatter. Positrons are antimatter. Means anti-electron actually. Okay. So positrons are used in case of PET scans, and that is the field of medical science. So antimatters are already in use, but not in the field of quantum computers. And scientists are dreaming of making quantum computers with the help of antimatters because there are so many advantages. Okay. Anyway, so scientists are always optimistic. And you know that history says what? Today's dream may become tomorrow's truth. Okay. If you study history, you know that thing. Anyway, so this was all about today's topic. Building quantum computers with antimatter. Okay. So this is the end of this video. Thank you. Thank you for watching this video.